Welcome to Civilization X. People rarely die from one thing called aging. Multiple cell repair systems fail at the same time. At 6:40 on a Tuesday morning, a 58-year-old school bus driver waits for her hands to unclench, hesitates before standing, forgets why she entered the kitchen, and hears her mother's last decade echoing forward. Global life expectancy reached 73.3 years in 2024. Healthy life expectancy is lower, so the real risk is not simply dying later. It is living longer while losing the strength, memory, balance, and independence that let a person keep working, driving, and choosing their own life. Aging labs, AI groups, and cell biologists are now attacking the same problem from different angles. Protein structure prediction, biomarker discovery, drug screening, and epigenetic age measurement. One of the strongest clues came from a 2023 Nature study on mouse retinal cells, where controlled partial reprogramming pushed damaged tissue toward younger function. The question is not whether cells change with age. They do. The hard question is whether science can reset enough of that damage to restore function without triggering cancer, tissue confusion, or years of expensive false hope. Aging is accumulated biological damage. DNA picks up errors, epigenetic marks drift, so cells read the right genome with the wrong settings. Mitochondria lose efficiency. Proteins misfold. Senescent cells stop dividing, but keep releasing inflammatory signals. Stem cell reserves thin out. In 2013, researchers organized this into 9 hallmarks of aging. In 2023, that framework expanded to 12. This is why aging is not one switch. It is a system failure across repair, energy, signaling, and regeneration. That is why the bus driver's stiff hands are not one disease. They are surface symptoms of deeper hallmarks accumulating underneath. Aging is also not fringe science. The 2009 Nobel Prize honored Elizabeth Blackburn, Carol Greider, and Jack Szostak for telomere biology, a core mechanism linked to cellular aging. The 2020 Nobel was for hepatitis C, not aging, which matters because this field still has to earn every claim. AI adds speed, not magic. DeepMind's AlphaFold database predicted structures for more than 200 million proteins, helping researchers map age-related pathways. Biological age models also build on clocks like Steve Horvath's 2013 system, which used 353 CPG markers to estimate tissue age. Then came the shock. In 2023, researchers reported that partial epigenetic reprogramming restored vision in aged and injured mouse retinal cells. Some old cells may still retain a recoverable record of youth. Full reprogramming can erase identity and raise tumor risk. Partial reprogramming tries to reset age without turning a retina cell into something else. So, what has been achieved? Real mechanistic progress, but no approved therapy that treats human aging itself. Regulators approve diseases, not aging as an indication. Mouse success is not human proof. Senolytics may remove harmful senescent cells, but those cells also aid wound healing and tumor suppression. AI can rank targets, yet biology stays noisy and causality hard to prove. By 2030, 1 in 6 people on Earth will be 60 or older, rising from 1 billion in 2020 to 1.4 billion. In the next 5 to 15 years, the engineering target is narrower than immortality. Validated biomarkers, safer reprogramming windows, and therapies that extend health span before frailty, dementia, and cancer dominate old age. Linda Partridge put it plainly: aging is the major risk factor for many chronic diseases. The open problem is now precise. How do we reset enough of a human cell's epigenetic age to restore function without crossing into cancer or loss of identity? The constraint is real. The data exists. Whether the systems built around it can act on it at scale, that is the next engineering problem. Stay with Civilization X.